All right, here we're going to do a little bit of review of some of our basic integration rules. And in order to kind of frame this, I want to look at these three integrals. The integral of 4 over x squared plus 9 dx, the integral of 4x over x squared plus 9 dx, and the integral of 4x squared over x squared plus 9 dx. Now, before I show you how to work out each of these three integrals, why don't you pause the video and see if you can figure out how you might integrate these. Cool, so I hope that you did pause and were able to figure maybe at least the first two out. Maybe you had a little bit of trouble with the third one, but let's take a look at each of these individually. So this first one is just a pretty straightforward inverse tangent integral where our u is x and our a is 3. And if you don't know what I'm talking about, we can set up the rule that the integral of du over the square root of no, I don't know what I'm doing. I'm going to leave that in the video just so you can see my little outtakes. All right, so our general formula is that du over u squared plus a squared is equal to 1 over a arctan u over a. So here, the integral of 4 over x squared plus 9 dx, here our u is equal to x, our a is equal to 3, because 9 is 3 squared, and that 4 is just behaving like a constant multiple. So this is just going to be 4/3 arctan x over 3 plus 3. So that one's pretty simple. All right, 4x over x squared plus 9, the only thing that we're going to need to recall here is the rule that the integral of dx over x is equal to the natural log of the absolute value of x. Hopefully you figured this one out, but let's work it out. So we're looking at the integral of 4x over x squared plus 9 dx. And this just involves a pretty straightforward U-substitution. So we're going to let u equal x squared plus 9. And so du is equal to 2x dx, or actually I don't want 1/2 because we actually have 4x dx, so I'm going to write 2 du is equal to 4x dx. And so what we have here is the integral of 2 du over u, which is equal to 2 times the natural log absolute value of u plus c. Here, because our u is always strictly greater than 0, x squared plus 9 is always strictly greater than 0, we can drop the absolute value in this case. And so we are just looking at 2 times the natural log of x squared plus 9 plus c. Don't forget the plus c. All right, there's no special techniques required, integration techniques that is, in order to compute this last one, but there is a little trick, and so I'm going to show you what that little trick is. So we have the integral of 4x squared over x squared plus 9 dx. Now, if you attempted this on your own before, maybe you tried to do a U-substitution and found that it just didn't work. And so what we're actually going to do here is a little algebra trick. So I'm going to start by pulling that 4 out in front. So I'm going to write this as 4 times the integral of x squared over x squared plus 9 dx. And the little algebra trick that I'm going to do is just the trick of adding 0. And so I'm going to write this as 4 times the integral of x squared plus 9, not minus x, minus 9 over x squared plus 9 dx. And hopefully you can see where I'm going with this now, because now what I can do is I can split this thing up into 4 times the integral of x squared plus 9 over x squared plus 9 minus 9 over x squared plus 9. And x squared plus 9 over x squared plus 9 is just 1. And so what we have then is 4 times the integral of 1 minus 9 over x squared plus 9 dx. And so hopefully we know how to integrate 1, right? That's just x. And then this negative 9 over x squared plus 9 reverts back to our first arctangent case where our u is x and our a is 3, and that 9 is just a constant multiple. So I'm looking at 4 times x minus, and what we have here is our constant multiple, but over a, times arctan of x over a, or u over a, in this case x over 3, plus a constant. And I'm going to go ahead and distribute my 4, and so I'm looking at an answer of 4x minus 12 times the arctangent of x over 3 plus a constant here. And that trick of adding 1 can really come in handy. So here, in this example, we added 1 in the form of just adding and subtracting a constant. But it can also come in handy in other problems. And so I'm just briefly going to look at one more just to show you an example of this. So let's say I wanted to compute the integral of 1 over 1 plus e to the x dx. Well, if we tried to do a U-substitution with this, we would probably start by letting u be 1 plus e to the x. But we know that no matter how many times we differentiate e to the x, it's never going to go away. And so what we kind of want is an e to the x in our numerator. So here I'm going to do basically the same little trick